Good morning. Today's topic is capacitive transducers, right? So, in the last class, we have seen some topics on uh, advantages of electrical transducers and what are the factors that influence while choosing a proper transducer for a particular application. So, in the last class, we have seen so many advantages of electrical transducers, right? Basically, instruments are classified as mechanical instruments, electrical instruments, and electronic instruments. So there are number of problems associated with instruments. So that we are moving on to electrical instruments for the purpose of measuring and controlling. So if I want to summarize uh, some disadvantages of mechanical transducers, let me put some points like mechanical transducers are very bulky. Okay, so they pose mass inertia problems. So and there are so many number of moving parts associated with mechanical instruments. So there will be frictional losses also. Since there are so many moving parts, continuous maintenance must be necessary in order to operate it smoothly. And there are since there are so many moving parts, speed of response is very less, right? And these mechanical instruments are much more noisy, and mechanical instruments doesn't serve me as their accuracy is less when compared to electrical and electronic instruments. And so due to this so many problems, of course there are some advantages also in using mechanical instruments. Designing of mechanical instruments is very easy. So in spite of their advantages, there are so many disadvantages also. If I want to automate a mechanical system, it is somewhat tough when compared to electrical and electronic instruments and electronic transducers. So mostly, I want to convert any physical parameter into voltage or current. For this, for this purpose, mechanical instruments doesn't serve me as as I am automating the system. So for the purpose of automation, I want to convert any physical parameter like temperature, pressure, viscosity, humidity, moisture, damping, speed, velocity, acceleration, torque, rotation, pH, conductivity, so on, into electrical signals. So I want to convert any physical parameter into electrical signals like voltage, current, and frequency, right? So what I want doing is I want to convert this into electrical signals such that the electrical signals are very easy to operate, very easy to maintain, and if I want to transfer information from one place to another place, I can easily transmit voltage and current signals than uh, mechanical signals like force, torque, and vibration, temperature, etc. I can't transmit temperature from one place to another place. I can't transmit pressure from one place to another place without drop. So if I if I if I want to send information or signal from one point to another point, it is easy for me to convert physical parameter, any physical parameter like temperature, pressure, viscosity, speed, velocity, acceleration, so on, pH, conductivity, so on, into electrical signal, such that I can transmit the electrical signals. Means if I want to measure this physical parameter, I will measure this in terms of current. So the the current I got at the output of sensor is a measure of input physical parameter. So this current signal I can transmit to long distances. I can amplify the signal if it drops its energy, and I can rectify a signal for my application to serve, and I can easily transmit from one place to another, and also I can make numerous operations on a signal like filtering, amplification, rectifying, and mixing, demodulating, modulating, so on. So without loss of signal, I can transmit if it is an electrical signal. So what I want to do is I have to convert all the physical parameters into electrical signals. So the instrument which does this is called electrical transducer or electronic transducer. So the functioning of electronic transducers or electrical transducers is to convert a non-electrical quantity into electrical signal such that it is easy for me to automate the input signal. Okay, so so basically electrical transducer does this for me. Okay, does this for me, right? And advantages of electrical transducers are electrical amplification and attenuation can be done easily. Means I can make any operation on a signal, like I can add two signals, I can subtract two signals, and I can mix two signals, and I can amplify a signal, I can rectify a signal, I can demodulate a signal. So if it is not in electrical parameter, then I can't uh, I can't modulate two pressure signals. I can't modulate two temperature signals. Okay, I can't modulate temperature. I can't modulate pressure. I can do this if if they are converted into electrical signals. So electrical amplification and attenuation can be done very easily with a static device, and the effects of friction is minimized because there are no moving parts inside the electrical transducer. So friction is greatly minimized, and the electric and electronic systems are controlled by a small electrical power. So in industries, I can operate any electronic device or electrical device with the help of 24 volts DC. Just 24 volts DC is the industrial standard to automate a process, right? So for the automation of process, just I will use 24 volts DC, and wherever necessary, I go for 230 volts if I am working on solenoid valves, likewise, right? So the electrical power is very much less used. A small amount of power is can be used, and it can able to control the total system. And the electrical power can be easily used, transmitted, and processed for the purpose of measurement. So any physical parameter can be converted into suitable electrical signal by using electrical and electronic transducers. So that's why I go for electrical electronic transducers, mostly industries for the purpose of automation, right? And in the last step, we have also seen what are the factors that are considered while setting a transducer. So accuracy must be high, precision must be high, and dead zone must be less. There must be no dead zone, and error is an unwanted characteristic for any instrument. If there are, but 100% I can't eliminate errors. But so if there is error, the error must be static, not dynamic error, right? So static error means error is constant throughout the measurement of the device, right? So and if the error is dynamic, then I can't assess the magnitude of error from measurement to measurement. Why? Because the error may vary rapidly from one measurement to another measurement. And an instrument must be high sensitive, optimal sensitive. Why? Because if the system has high sensitive, then I have to compromise for stability. And if the system is less sensitive, it may pose errors for me. So in order to eliminate errors, in order to eliminate errors, accuracy, sorry, sensitivity must be optimum. Sensitivity must be optimum. So if the sensitivity is optimum, then it can pose somewhat small errors, but I can overcome these errors by proper calibration. And the instrument should be highly reproducible and highly repetitive. Okay, repeatability and reproducibility are two major concerns while selecting a transducer. And accuracy, precision, resolution are also wanted characteristics is selection of a suitable transducer or suitable instrument for a particular measurement. And environmental capability also plays a major role in giving proper values, right? And the instrument must withstand high loads, means it must be reliable. So the instrument must have high reliability, means it must have the ability to withstand loads. Okay, and the instrument must have high resolution such that the smallest deviation in the input can also be measured. So the sensitivity must be optimum throughout the device and linearity must be there throughout the device, right? So if sensitivity is constant at all points of the measurement, then the system is linear, right? And the system must have high input impedance and low output impedance in order to avoid loading effect. So these are the characteristics I have to consider while selecting a proper transducer for a measurement, right? And the requirements must be small in size, good sensitivity, and environmental capability and low cost. In spite, the instrument have some characteristics like fidelity and speed of response also, right? Fidelity and speed of response are also the characteristics which you have to consider by selecting a transducer. Okay, speed of response means the rapidity with which the instrument responds to the input and gives output is called speed of response. And sensitivity is the ability of system to respond for the smallest change in the input. So sensitivity and speed of response must be made good while selecting a transducer or an instrument for the purpose of measurement, right? And today's topic is capacitive transducers. Capacitive transducers, right? So, so in the last class, in the previous class itself, we have seen some concepts like classification of transducers. Classification of transducers. So I told you at that time, in this unit, we're going to study all this classification in depth. Okay. So I'm moving on to this first classification based on the principle of transduction. Okay. In the last couple of classes, we have seen what is on what basis uh, on what basis the instruments are classified on the basis of transduction. Okay, so so if the instrument uses capacitive principle, if the instrument uses capacitive principle to measure the input signal, then it is called capacitive transducer and it is called capacitive transduction. So let us move on to capacitive transduction now. So this first classification we will study a lot in this unit. Okay, so I'm moving on to first classification, that is capacitive transducer. So as I said, capacitive transducer is an instrument which gives output due to changes in its capacitance. So, so if I want to, for example, if I want to measure pressure by the capacitive transducer, then this sensor or this transducer or this pickup will give output depending upon changes in its capacitance for the input applied. Okay, for example, what is a capacitor? Capacitor consists of two parallel plates. Okay, this is one parallel plate of a capacitor and this is another parallel plate of a capacitor. Okay, and in between these two plates there may be a dielectric. Okay, if there is no dielectric, then air behaves as a dielectric between the two plates, right? So this is a symbol for capacitance. So a capacitor consists of two conductors are electrically isolated by one another. Okay, and in the middle I can place a dielectric material also. In case if there is no dielectric material, if there is no dielectric material, then air acts as dielectric. Okay, generally there may be a dielectric here, between these two plates, right? So when the two conductors are at different potentials, the system is capable of storing electric charge. The storage capacity of capacitor is measured in farads. And the principle of operation of capacitive transducers is based upon equation for capacitance of a parallel plate, likewise, as shown in this figure, right? Now, capacitance C equal to epsilon A by D is the basic formula, right? Capacitance C equal to capacitance C equal to epsilon A by D, epsilon A by D, where D is the distance between the two parallel plates of a capacitor, distance between two overlapping plates of a capacitor, and D is the distance between two parallel plates of a capacitor, and A is the overlapping area here. A is the overlapping area of a capacitor, and epsilon is permittivity, where epsilon can take the form epsilon equal to epsilon naught and epsilon r. Epsilon naught equal to epsilon naught into epsilon r, where epsilon r is relative permittivity, and epsilon r value is equal to epsilon r equal to 1 if it is 8. Then if there is a dielectric material placed here, if there is a dielectric material placed here, then epsilon equal to epsilon naught into epsilon r. So, one second, I'm getting sound from outside. I will close the door. Excuse me. Okay. So here, epsilon equal to epsilon naught into epsilon r. And if there is no dielectric placed in the place between two parapet of a capacitor, means there is one plate of a capacitor and is another plate of a capacitor, and I am not using any dielectric material in between these two electrically isolated, insulated parallel plate capacitor. Then capacitance C equal to epsilon naught. Capacitance C equal to epsilon naught A by D. Epsilon naught A by D, where here for 8 epsilon naught becomes 1. Therefore, epsilon r becomes 1. Then I will get epsilon equal to epsilon naught. Therefore, capacitance C equal to epsilon naught A by D is my formula for parallel capacitor with air as a dielectric material. And if the dielectric material present, then capacitance C equal to epsilon naught and epsilon naught into epsilon r A by D. Epsilon naught A by D. Okay. This is epsilon naught, not epsilon B here. It is epsilon naught. Okay. Epsilon naught, epsilon r A by D, and epsilon naught have value depending upon the dielectric material which I am using here between the two parallel plates of a capacitor. Okay, so C equal to epsilon A by D, where A is the overlapping plates and it is expressed in meter square, and D is the distance between the two plates and its unit is meter, and epsilon is permittivity. It's a dielectric constant. So let us suppose the top plate of a capacitor and this is the bottom plate of a capacitor separated by a dielectric material. Okay, therefore C equal to epsilon A by D, right? And if I want to, so here, if I want to tell about voltage between the plates of a capacitor, then voltage V equal to Q by C. Voltage equal to charge by capacitance. Okay, I will take a text box here. Voltage V, voltage V equal to Q by C. Q by C, where Q here is charge and C is the capacitance. Okay, where C here is epsilon A by D. C here is epsilon A by D. So V equal to Q by C. This is the voltage that is accumulated inside the capacitor. And if I want to measure current here, current I equal to C del V, C del V. Okay, or C into del V here means dV by dt, dV by dt. So I equal to C into dV by dt. This is the current. Okay, and Q equal to CV, Q equal to CV or V equal to Q by C is the voltage across the capacitor, parallel plate capacitor, right? So how I will use this parallel plate capacitor in measuring inputs? Okay. So let us suppose I want to measure humidity. I want to measure humidity. Okay. So I'm using a bit circuit here. I'm using a bit circuit here. This is the resistance. This is under resistance with the capacitor in parallel to it, and this is under resistance. And here I'm using a resistor in series with a capacitor, and here I'm applying some voltage. I'm applying some voltage here. I'm applying some voltage here, and here I am placing a meter. I'm placing a meter here. So let us suppose this is the bridge circuit. Okay, and the impedance here I call is Z1. Impedance here I call it is Z2. Impedance of this branch I call it Z3. Impedance of this material I call Z4. Impedance of this RC network, RC branch, I call it Z4. Okay. In the initial condition, Z1 equal to Z2 equal to Z3 equal to Z4. When Z1 equal to Z2 equal to Z3 equal to Z4, bridge is balanced. Okay, this is sine wave supply. This is sine wave supply. Okay, I am going to supply here, voltage supply here. E is the voltage I am applying here, and this is the meter. Okay, this is the meter. So Z1 equal to Z2 equal to Z3 equal to Z4. So the bridge balancing condition is Z1 opposite branch products must be equal. Z1 Z4 Z1 Z4 equal to Z2 Z3 Z2 Z3. So Z1 Z4 equal to Z2 Z3. Okay, let us put in neat form like this. Okay, the bridge balancing condition is Z1 Z4 equal to Z2 Z3 is the bridge balancing condition. Okay, when Z1 Z4 equal to Z2 Z3, then the bridge is balanced such that I will get no current here in the meter. I will get no current here in this meter. Okay, current equal to 0. Why? Because current entering this side and this side is equal, and both are in opposite directions such that they will cancel each other and current equal to 0. So this is the condition where it is balanced, right? And I'm using this capacitor to measure humidity. Okay, how let us suppose this is the capacitor Z4, which I am taking now. This is a capacitor Z4. Okay, and in between the two parallel plates, I'm using a dielectric material. I will use here a dielectric material, right? I'm using here a dielectric material, and for measurement of humidity, I will use hygroscopic salts. Hygroscopic salts means these are salt materials which are sensitive to humidity. Example NaCl. Okay, మన ఇంట్లో వాడుకునే ఉప్పు అండి. ఉప్పు ఏమవుతుంది ఇన్ వింటర్ సీజన్ ఆర్ రైనీ సీజన్ ఉప్పు ఏమవుతుంది అంటే వాతావరణంలో ఉండే తేమని పీల్ చేసుకొని అది కూడా మెత్తగా అయిపోతుంది. ఉప్పు పొడి పొడి రాలుతూ ఉండదు. ఉప్పు కూడా బాగా తడిగా ఉంటుంది ఉప్పు కూడా. ఓకేనా? సో ఇనిషియల్లీ here NaCl కామన్ సాల్ట్ అనేది ఏంటి అంటే ఇట్ ఇస్ ఎ hygroscopic salt. It can measure humidity. Okay, it can absorb moisture. So previously, I'm using here two parallel capacitor. In between two parallel of a capacitor, I'm using a dielectric material which is a hygroscopic salt. Hygroscopic salt I'm using here. Okay. Previously, I am not applying any humidity for this salt. ముందుగా దీనికి ఎటువంటి హ్యూమిడిటీ అప్లై చేయలేదండి. దెన్ వాట్ విల్ హ్యాపెన్ అంటే ఇది బాగా పొడి రాలుతూ ఉంటుంది అనమాట. ఈ సాల్ట్ ఈ మధ్యలో పెట్టిన సాల్ట్ అనేది ఏమవుతుంది అంటే బాగా పొడి రాలుతూ ఉంటుందండి. ఓకే, బాగా పొడి పొడిగా ఉంటుంది అనమాట. మీన్స్ there is no moisture content here. So what will happen? What will happen? The impedance the impedance of this capacitor అన్నది మనకి కాన్స్టెంట్ గా ఉంటుంది, మారదు. ఓకే, ఇంపిడెన్స్ Z of capacitor is constant and it will not vary. Okay, right? Let us suppose I am inserting this capacitor into a chamber whose humidity I want to measure. Okay, let us suppose I'm inserting this capacitor into a chamber whose humidity I want to measure. Okay, so when I insert this capacitor into a chamber whose humidity I want to measure, then what will happen? This salt inside the capacitor will absorb humidity present in the chamber. Okay, then what will happen? This salt becomes conductive. The salt becomes conductive and Z varies. Z reduces. Value of Z reduces. Means ఇక్కడ నేను సాల్ట్ పెట్టానండి. ఒక హైడ్రోస్కోపిక్ సాల్ట్ అన్నమాట ఇది. ముందుగా ఇది బాగా పొడి పొడిగా ఉంది. There is no moisture here, content here inside this salt. Then what will happen? It acts as the insulator. Just as insulator కి యాక్ట్ చేస్తుంది. ఓకే, కాబట్టి let us suppose Z is the impedance of this capacitor. Okay, సో ఇప్పుడు ఏమవుతుంది అంటే ఏ చాంబర్ లో నేను హ్యూమిడిటీ కనుక్కోవాలనుకుంటున్నానో ఆ చాంబర్ లో దీన్ని capacitor తీసుకెళ్ళాను. అప్పుడు ఏమవుతుంది? సాల్ట్ అన్నది హ్యూమిడిటీని పీల్చుకుంటుంది, మాయిశ్చర్ని పీల్చుకుంటుంది. పీల్చుకున్నప్పుడు ఏమవుతుంది? ఇది కొద్దిగా తడివారుతుంది. అప్పుడు రెసిస్టెన్స్ మారిపోతుంది కదా. వై? బికాస్ బాగా తడిబారిపోయింది. So it is absorbing moisture. So what will happen? It absorbs moisture and it will become conductive salt. అప్పుడు Z ఏమైపోయిందండి? డిక్రీస్ అయిపోతుంది. ఓకే, రెసిస్టెన్స్ ఆఫర్డ్ బై దిస్ కెపాసిటర్ ఇంపిడెన్స్ Z అనేది ఏమవుతుందమ్మా? తగ్గిపోతుంది. It will reduces. Okay, when Z reduces, Xc means reactance of a capacitor. Xc equal to 1 by 2 pi Fc is my formula. 1 by 2 pi Fc is my formula. Right? So ఇక్కడ dielectric మారిపోయిందండి. ఇప్పుడు the properties of dielectric will change here. Why? Because this dielectric material is absorbing humidity. Then what will happen? Previously capacitance C equal to epsilon naught or simply epsilon రాస్తానండి ఇక్కడ నేను. Epsilon A by D, where epsilon is permittivity of this dielectric material. Okay, so now what will happen? This dielectric material is absorbing moisture, and what will happen? This epsilon will vary. When epsilon varies, then capacitance C value reduces or increases depending upon this epsilon value. If capacitance changes, what will happen? Xc equal to 1 by 2 pi Fc. If capacitance changes, then what will happen? Xc also varies. Xc కూడా మారిపోతుంది. When Xc varies, then what will happen? Z4 will vary. Okay, Z1, Z2, Z3 Z1, Z2, Z3 have normal values, and Z4 is varying now. If Z4 varies, then Z1, Z4 is not equal to Z2, Z3. Then what will happen? The current induces here. The current in the meter will be induced. The current in the meter will be induced here. The current induced here. Why? Because it is now unbalanced. Now, the amount of current which the meter is showing, amount of current is proportional to humidity in the chamber. Likewise, I will measure humidity. I will measure humidity in terms of current. In terms of current. Likewise, I will use capacitance transducers. So here, how I will how I can use capacitance transducers to measure various inputs. Not only measurement, capacitance transducers are also used to measure humidity, humidity, moisture, humidity. Okay, it is used to measure humidity, moisture. Okay, displacement, humidity, moisture. Okay, humidity, moisture, displacement, level, liquid level, liquid level, pressure, so on, so on, so on. So mainly a flow rate. Okay. So humidity, moisture, displacement, liquid level, pressure, flow rate are the applications in which I will use this capacitor reducer to measure the input signal, and this will give me electrical output in terms of current, and this current is a measure of input which I have applied. And if the moisture varies, then the output current also varies. The moisture varies, then output current also varies. So likewise, I will measure my input parameter, okay, in terms of current, right, by using capacitance reducer, okay. And Z equal to, just now I have told you, the capacitance is measured with bit circuits, right? Just now I have told you. The output impedance Z of a capacitor transducer is Z equal to 1 by 2 pi fc, where 2 pi is a constant, f is the frequency of input signal which I have applied, okay, and C is the capacitance, right? In general, output impedance of a capacitor transducer is very, very high, right? This fact calls for careful design of the output circuitry. The capacitor transducers work on the principle of changing capacitance of a capacitor. This changing capacitance could be caused by changing overlapping area of plates, changing the electric potential, and changing the distance between the two plates also. Okay, as I said, C equal to epsilon A by D. Capacitance varies. Capacitance varies if I vary this permittivity, or if I vary overlapping area of plate, or if I vary distance between the two plates. Okay, so if the distance between two plates is varied, if the distance between two plates is varied, then capacitance can be varied. And if the overlapping area of two plates is varied, then capacitance will be varied. And permittivity, epsilon, if epsilon varies, then also capacitance will vary. So depending upon the application, I can uh, bring changes in these values, epsilon, A, or D, such that the capacitance is varied. Okay, let us suppose I want to measure displacement. Okay, this is a fixed plate and this is a movable plate. This is a fixed plate and this plate is a movable plate. This plate is a movable plate. Okay, for example, I want to measure displacement. So I am giving displacement to this movable plate. To this movable plate. Let us suppose displacement direction is like this. Okay, displacement direction is like this. Then what will happen? What will happen? This plate will move like this. Will move like this. Why? Because I'm applying displacement in this direction. So the plate, the second plate of a capacitor will move towards first plate of a capacitor. Then what will happen? the distance between the two plates is now the distance between the two plates is now decreased. Two plates is now decreased. So if distance decreases, what will happen? Capacitance increases. If I use capacitor in the bit circuit which I have shown earlier, then it shows me the output is induced. The output current is a measure of displacement. Okay. Or let us suppose this is a first plate of a capacitor and it is a fixed plate and this plate is a movable plate. This plate is a movable plate. For example, I want to measure displacement. Again, displacement I want to measure. So what I will do? I will apply displacement like this to this movable plate. Then what will happen? If displacement is in this direction, then what will happen? This plate, I will show you with another tool. Okay, this is a plate of a capacitor. Sorry, how can I show you? Right. Okay, there is a first plate of a capacitor, and this plate is a movable plate. Right. This is fixed plate, and the displacement is in this direction. Then what will happen? This second plate will move in this direction, such that let us suppose I'm applying displacement like this. Then this plate now came to this position. Okay. Then what will happen? Means the overlapping area of two plates is reduced now. Okay. In previous case, these are the plates of capacitor. Okay. So what is the overlapping area? Till this plate, this end to this end. ఈ ప్లేట్ కి ఇది మొత్తం ఓవర్లాపింగ్ ఏరియానే, మొత్తం ఓవర్లాప్ అయిపోయి ఉన్నాయండి. ఓకే. బట్ హియర్ to this part of place, to this part of plate, up to this part of plate, sorry, up to this part of plate, I don't have plate here, second plate here. So it doesn't act as a capacitor. And till this part, this plate has no second plate here. So from this point to this point, from this point to this point only, there is a overlapping area between the two plates. Then what will happen? Overlapping area is reduced now than in previous condition. So if overlapping area reduces, what will happen? Capacitance decreases. If capacitance decreases, Xc equal to 1 by 2 pi Fc. If capacitance reduces, what will happen? Reactance increases. Then what will happen? Bridge becomes unbalanced. The output current is a measure of displacement applied. So in this case, I am using change in overlapping area. In the previous case, I used change in distance between the two plates. Okay. Now, let us take a same example. I want to measure displacement. Now, what I am doing is, I am changing this epsilon, means permittivity I am changing. Okay. I am changing this epsilon. Okay. These are two plates of a capacitor. These are the two plates of a capacitor. Both plates are fixed now. Okay. And now this is my dielectric material. Right? And now, means this is a dielectric material placed between the two plates of a parallel plate capacitor. Now, what I am doing is, I am applying displacement now to this dielectric material. I want to measure displacement. So I am giving displacement to this dielectric material. So what will happen? Displacement is towards this direction from right to left. The displacement is. So what will happen? What will happen means as the displacement as as the displacement is towards left direction, what will happen? This dielectric material will move towards left side, towards left side. So so now due to applied dielectric due to applied displacement, now the dielectric material is now like this. Okay, so I'm applying displacement here. Okay, I'm applying displacement here. Okay, so due to displacement, that the dielectric material push it towards left side. So what will happen? What will happen? Capacitance varies. Why? Because from this point to this point, from this point to from this point to this point. Okay, this is a parallel, this is a plate, this is a plate. I have parallel plates, I have two parallel plates here. So that is the capacitor. But from this point to this point, air air acts as dielectric. Air acts as dielectric. From this point to this point, from this point to this point, between these two parallel plates, I have dielectric material. Okay, so what will happen? For this, from this point to this point, I call capacitance C1. From this point to this point, I call capacitance C2. So what is C1 now? C1 equal to epsilon naught epsilon r A by D. This is C1. What is C2 now? C2 equal to epsilon naught A by D. C2 equal to epsilon naught A by D. Why? Because epsilon r for air is 1. So it's not A by D. So what is the total capacitance? C1, C2 by C1 plus C2, C1, C2 by C1 plus C2 will be the total capacitance C of a capacitor now. So now C is varying. Previously, what is the capacitance? So this is the plate, and I have dielectric from this point to this point. So there is no air gap for parallel plates. So what is C previously? Previously C equal to epsilon naught epsilon r A by D. Epsilon naught epsilon r A by D is the value of C for this capacitor. And after applying displacement, what is the value of C? C1, C2 by C1 plus C2. Okay, so capacitance C is varied. But capacitance C is varied, then what will happen? Which becomes unbalanced. Xc varies such that which becomes unbalanced, and I will get output. That output is proportional to the input which I have given. Whether it may be pressure, or it may be a force, or it may be a some displacement, or it may be a liquid level, anything. So depending upon epsilon, and depending upon variations in epsilon and variations in A and variations in D, I can vary capacitance such that the varied capacitance will give me the resultant output. Okay, so here I am measuring displacement due to change in capacitance. That's why it's called capacitive transducer. That's why it's called capacitive transducer. Okay, so these are the points I have summarized here. Okay, so capacitance due to change in overlapping area of plates means A. Capacitance due to change in distance between two plates, that is D. Capacitance change in capacitance due to change in dielectric material, that is epsilon. Okay, so these are three modes in which I can change capacitance such that the variation in capacitance gives me the output, right? So this I have told you now, right? So cathode distance using is area of plates. Okay, epsilon A by D. A is length into breadth, so L W by D. So what is sensitivity of capacitor that uses changing area of plates is S equal to dou C by dou L. Dou C by dou L. So it becomes epsilon W by D. Epsilon W by D is the sensitivity, right? Keep in mind that the accuracy of capacitor transducers is very, 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 very high. Okay, so accuracy is as high as point not 5%, right? So if if I use capacitor transducers to measure liquid level, I can measure down to 1/100th of a millimeter also. Okay, so if I use if I use transducer, capacitor transducer, if I use capacitor transducer that uses change in distance between two plates, then sensitivity is epsilon A by D square minus epsilon A by D square. It is a sensitivity, right? And if I use change in electric constant, then I can measure up to a small distances also, small displacements also. So changing dielectric material gives me the measurement from zero point 0.1 into 10 power minus 6 mm also. Okay, so I can measure very, 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 very small measurements also, right? So where it is used, where I can use this capacity transducer means I can use capacity transducer to measure displacement, to measure liquid level, to measure force, to measure uh, humidity or moisture, okay, to measure angular displacements, etc., etc., etc. So, displacement, pressure, flow rate, liquid level, and then humidity, moisture. So, these are the applications of capacitor transducer, which I use much more. So what are the advantages of this capacitor transducers? Means it have high sensitivity, okay, and the capacitor is useful for small systems also, right? And it has very high frequency response, and it requires very small operating voltages. The loading effect is very, very low due to its high input impedance, right? And some of the disadvantages are it is temperature sensitive, and sometimes it may give long-range behavior depending upon the application. And output impedance depends on frequency used. This is a major disadvantage for me. And capacitance may get changed by dust particles and moisture, which produces some error. And this I can't take into account because it is very, 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 very rare case. Okay. So where I will use it? So I will use this capacitance transducer to measure humidity, to measure moisture, to measure liquid level, to measure density, to measure linear and diagonal displacements. Okay. In these cases, to measure differential pressures also, and use it to measure pressure, and flow rate also to measure flow rate of a s- particles like steam, water, gases, liquid, etc., etc. So these are all the applications in which I will use capacitive transducers much more. Okay. So in the next class, we would like to discuss about resistive and inductive transducers as well, so that the first classification may be completed as soon as possible. Okay, right? So till now we are discussing this first classification only. Okay. So in the next class, we will go for resistive type and inductive type transducers. Okay. So this is all for this class, and we will continue the next topics in next class.